I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College. This is the lecture 2 of Module 10. In my previous lecture, that means in lecture 1 of Module 10, I already discussed about the Maxwell's velocity distribution law, root mean square velocity, average velocity, and most probable velocity. And I already shown the velocity distribution plot of Maxwell's velocity distribution law. And now today I will discuss on degree of freedom, law of equipartition of energy, and specific heat of gases. Now what is degree of freedom? Degree of freedom. Now the degree of freedom is the total number of independent quantities, which are necessary to specify the configuration of any dynamical system. This is called degrees of freedom of the system. I repeat again, the total number of independent quantities, the total number of independent quantities, number of independent quantities that are necessary, which are necessary to specify, completely specify any dynamical system, any dynamical system is called degrees of freedom, degrees of freedom of the system, degrees of freedom of the system. So it is the number, actually the degrees of freedom, the total number of independent quantities which are necessary to completely specify any dynamical system is called degrees of freedom of the system. Suppose a marble is moving on the floor. That means this is a floor and a marble is moving in this direction, suppose in this direction. So we can say that the degrees of freedom of this dynamical system is 2, because 1/4 is x direction and 1/4 y direction. This is x direction suppose, and this is y direction. That means only the 2 components are required to specify the configuration or specify any dynamical system. So this is only 2 independent parameters or independent quantities are required to specify the configuration or the movement of the marble. Therefore we say that for a particular marble now which is moving on a floor, that means only two direction they can move, x direction or either direction. Therefore, the degrees of freedom is 2. This is the degrees of freedom. Suppose, and another example, if a mosquito is flying in the room or in a room, therefore the mosquito move in any direction, that means in x direction, in y direction, or in z direction. That means for this particular example the degrees of freedom is 3. Suppose, and another example, an electric fan is moving, so the minimum number of degrees of freedom is 1, only the rotation angle. That means for a particular moving electric fan, the minimum number of degrees of freedom is equal to 1, only the rotational angle. So these are the example of degrees of freedom of the system. I repeat again, what is the degrees of freedom? Degrees of freedom is the total number of independent quantities which are necessary to completely specify any dynamical system is called degrees of freedom of the system. Now, with the degrees of freedom, I have to know generalized coordinate. Generalized coordinate. Generalized coordinate. Generalized coordinate. What is generalized coordinate? What is generalized coordinate? The coordinate associated with each degree of freedom is called a generalized coordinate. The generalized coordinate, generalized coordinate associated is that, the generalized coordinate is that each associated with each degrees of freedom. The generalized coordinate is that the coordinate associated with each degrees of freedom, associated with each degree of freedom, and this is called generalized coordinate. That means the coordinate associated with each degrees of freedom is called generalized coordinate. Now another thing is constant. T-R-A-I-N, constant. Now what is constant? Constant is that the restriction imposed on the motion of a dynamical system are called constant of the system. What is constant? The restriction on the motion of a dynamical system, the restriction or limitation, the restriction imposed or limitation imposed on the motion of a motion of a dynamical system, dynamical system is called or are called are called the restrictions or limitations imposed on the motion of a dynamical system are called constraint of the system. Constraints of the system are called constant of the system. So constant means the restriction or limitation imposed on the motion of a dynamical system. Now suppose a system is consist with n free particles. Suppose a system is consist with n free particles. Therefore, the total number of degrees of freedom is 3n. This is degrees of freedom. Degree of freedom. Degrees of freedom is 3n. The number of particles is n. This is the number of particles. Number of particles. Number of particles is n, and 3n is the degrees of freedom of the system. Yes, n number of particles is n and 3n is the number of degrees of freedom of the system. And if there are k number of restriction or limitation or constants, then the degrees of freedom of the system, effective degrees of freedom of the system is effective degrees of freedom degree of freedom equal to f equal to 3n minus k, where f is the degrees of freedom. F is the degree of freedom. That means n is the number of particles. So if n is the number of free particles, then total number of degrees of freedom is 3n. And if k is the number of constant imposed on the motion of these n number of particles, then the degrees of freedom f equal to 3n minus k, where k is the number of constant. Now the law of equipartition of energy. 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 Here I only keep the statement of equipartition of law of equipartition of energy, only the statement. This law states that the energy of a dynamical system, in thermal equilibrium is equally divided into its different degrees of freedom. I repeat again, this law states that the energy of a dynamical system in thermal equilibrium is equally divided into its different degrees of freedom, and the energy per degrees of freedom is equal to half kT, where k is Boltzmann constant and T is the absolute temperature of the system. So this law states that the energy of a dynamical system, the energy of a dynamical system in thermal equilibrium is equally divided is equally divided into equally divided into its different degrees of freedom, into its different degrees of freedom, different degree of freedom, and the energy per degrees of freedom, the energy per degree of freedom, per degree of freedom is equal to half kt, half kt, where k is Boltzmann's constant, where k is Boltzmann's constant, k is Boltzmann's constant, Boltzmann constant, and T is the absolute temperature of the system, absolute temperature, absolute temperature of the system, absolute temperature of the system, of the absolute temperature of the system, of the system. This is the law of equipartition of energy. I repeat again, this law states that the energy of a dynamical system in thermal equilibrium is equally divided into its different degrees of freedom, and the energy per degrees of freedom is called per degree of freedom is equal to half kt, where k is Boltzmann's constant and T is the absolute temperature of the system. Now, some applications. The degrees of freedom and the specific heat. Degrees of freedom, some application of law of equipartition of energy. Applications. Law of equipartition of energy. Applications of law of equipartition of energy. Suppose a system of free particles is having f degrees of freedom. F degrees of freedom. Suppose a system of free particle each having f degrees of freedom. F degree of freedom. That means degree of freedom equal to F. The energy per degree of freedom equal to half kt. Energy per degree of freedom equal to half kt. So the energy of the system per gram mole is half kt per degrees of freedom. If F is the number of degrees of freedom, therefore F into half kt, and if N is the number of mole, then the total energy of the system equal to half kt into F into N. Okay, clear? The energy per degrees of freedom equal to half kt. So it has F degrees of freedom, that means F into half kT, and n number of moles, that means it becomes half kT into F into n, where it becomes half R F and T, where R equal to n into k, n into k. R is the constant. Therefore, here we write Cv equal to dE dt at constant V equal to half R F, half R F, half R F. Now since Cp minus Cv equal to R, Cp minus Cv equal to R, then Cp equal to R plus Cv equal to R plus half Rf, Rf equal to R times 1 plus F by 2. Therefore, gamma, the specific ratio of two specific heat, gamma equal to Cp by Cv equal to Cp by Cv equal to R into 1 plus F by 2 divided by half Rf, half R into F. That means it becomes 1 plus 2 by F, 1 plus 2 by F. That is gamma equal to Cp by Cv equal to 1 plus 2 by F. This is the relation between ratio of two specific heats and degrees of freedom of the system. Suppose for monatomic gas, I have to calculate the gamma, that means the ratio of two specific heats of monatomic gas. Case 1, suppose case 1 monatomic gas, monatomic gas. Here for a monatomic gas, the degrees of freedom equal to the degrees of freedom F equal to 3, and there is no restriction. So the degrees of freedom becomes F equal to 3n minus k, 3n, sorry, here I just put here n equal to 1. Monatomic gas, n equal to number of gas molecule equal to 1, constant is 0, this is 1, this is constant, no constant, k equal to 0. That means degrees of freedom equal to 3 into 1 minus 0, that means 3. So for monatomic gas, the ratio of two specific heats, gamma equal to 1 plus 2 by F. That means 1 plus 2 by 3 equal to 1.66. Therefore, gamma for monatomic gas equal to 1.66. This is the gamma of monatomic gas. Second case 2, diatomic gas. For diatomic gas, n equal to 2, number of constant equal to 1. Now why the number of constant is 1? Because the diatomic molecule, the distance between two gas molecule is fixed to atom diatomic gas. That means the distance between two atoms in the diatomic gas is always constant. Therefore, we get the number of degrees of freedom F equal to 3n minus k. That means 3 into 2 minus 1. That means 6 minus 1 equal to 5. So, for diatomic gas, gamma equal to 1 plus 2 by F. That means 1 plus 2 by 5 equal to 1.4. So, for diatomic gas, gamma becomes equal to 1.4. Now, this is case 2. This is case 2, and now case 3. Case 3, triatomic molecule. Triatomic molecules. Here, for linear triatomic molecule, n equal to 3 and k equal to 2. That means F equal to 3n minus k. That means 7. Therefore, gamma equal to 1 plus 2 by 7 equal to 1.28. And for triatomic molecule, triangular shape, linear shape and triangular shape. Triangular triatomic molecule, n equal to 3, k equal to 3. That means F equal to 3 into 3 minus 3 equal to 6. Therefore, gamma equal to 1 plus 2 by 6. That means 1.33. So, these are the applications of degrees of freedom with the help of law of equipartition of energy. And here we calculate the gamma, that means Cp by Cv of linear, monatomic, diatomic and triatomic gas molecules. Now, the specific heats. I want to define the specific heat of gas. Specific heat of gases. Specific heat of gases. Before going to discuss the specific heat of gas, I will say first the heat capacity. What is heat capacity? Heat capacity. Now before going to define the specific heat of gas, first of all I want to discuss what is heat capacity. Heat capacity of any material. Heat capacity. The heat capacity is the differential. Different materials have different heat capacity. That means different materials have different heat capacity to absorb heat to produce a given change of temperature in a given mass. I repeat again, different materials have different heat capacity to absorb heat to produce a given change of temperature in a given mass. That means if a material of mass m absorb heat delta Q so that its temperature rises through delta T, then heat capacity is defined as delta Q divided by delta T. This is the heat capacity. That means different materials have different capacity to absorb heat to produce a given change of temperature in a given mass. If a material of mass m absorbs heat delta Q and its temperature rises delta T, then heat capacity is defined as delta Q by delta T. This is the heat capacity. Okay. Now specific heat. What is specific heat? What is specific heat? Specific heat. I proceed just one by one step. First of all, what is heat capacity? That means heat capacity is delta Q by delta T. What is specific heat? Specific heat is the heat capacity per unit mass. That means heat capacity per unit mass is known as specific heat. Heat capacity per unit mass. Heat capacity per unit mass. This is known as specific heat. That means specific heat, SP dot means specific heat. Specific means heat capacity divided by heat capacity divided by mass. That means delta Q divided by m into delta T. This is the specific heat. Now the definition is the specific heat of a material. It may be liquid, solid or gas, anyone. The specific heat of a material is defined as the quantity of heat required to raise the temperature of unit mass of the material through 1 degree. What is the definition of specific heat? The specific heat of any material is defined as the quantity of heat required to raise the temperature of unit mass of the material through 1 degree. This is specific heat. That means its unit specific heat, the unit of specific heat is calorie per gram per degree centigrade, or joule per kg per degree centigrade. Calorie per gram per degree centigrade or joule per kg per degree centigrade. This is the unit of specific heat. Now this is the specific heat of any material. This is the in general definition of specific heat. Now for gaseous system there are two types of specific heat. One is for constant volume and one is for constant pressure. Specific heat of gas. There are two types of specific heat for gas. There are two types of specific heat of gas. One is for constant pressure and one is for constant volume. One is constant pressure and other is constant volume. Constant volume. This is called constant pressure, means Cp, and this is Cv. This is constant P and this is constant V. The specific heat at constant pressure. Specific heat of gas at constant pressure. This is defined as the amount of heat required to raise the temperature of unit mass. The amount of heat required to raise the temperature of unit mass of a gas. Temperature of unit mass of a gas through 1 degree centigrade and when pressure is kept constant. Its pressure is kept constant. This is known as specific heat at constant pressure. That means Cp equal to delta Q divided by delta T at constant pressure. This is called specific heat of gas at constant pressure. That means heat required to raise the temperature of unit mass of a gas through 1 degree, and when its pressure is kept constant, this is called specific heat of gas at constant pressure. Now, the specific heat of gas at constant volume. Specific heat of gas at constant volume. This is CV. The definition is all same only when its volume is kept constant. That means the amount of heat required, the amount of heat required, the amount of heat required to raise the temperature of unit mass, temperature of unit mass temperature of unit mass of a gas through 1 degree centigrade when its volume is kept constant. When its volume is kept constant. This is specific heat of constant volume. That means delta Q by delta T at constant V. This is the specific heat at constant volume of gas. Specific heat of gas at constant volume. Here, since two types of specific heat, one is constant pressure and one is constant volume, it is obvious that the specific heat of constant pressure, the specific heat of constant pressure of a gas is always greater than the specific heat of gas at constant volume, because for a constant pressure of a gas, the more amount of heat is required to raise the temperature of the system or of the gas, because during this process the gas also doing some work. That's why more amount of heat is required to raise the temperature of the gas or to raise the 1 degree centigrade temperature of the gas at constant pressure. That's why at constant pressure Cp, that means the specific heat at constant pressure, is always greater than the specific heat at constant volume.